You have papers for me. Please send them to your left. Thank you. At the end of our discussion of the shortcuts, I laid down a couple of examples and said, I have other functions I don't know how to deal with. Things like these. This is actually the page from those notes. But we start with a product I already understand. I've got x squared. What's the derivative of x squared? Derivative of x cubed. What's the derivative of x cubed? So if I were to take x cubed times x squared, I get x to the fifth. What's the derivative of x to the fifth? Louder. 5x to the fourth. But if I take f prime of x times g prime of x, that's 2x times 3x squared, and that is definitely not the same thing. So while I'm happy to say that when I take the derivative of something that's been added, I just add the derivatives. When I take the derivative of something that's been subtracted, I just subtract the derivatives. When I take the derivative of something that's been multiplied by a constant, I just leave the constant. When I take the derivative of two functions multiplied together, I cannot take the derivative of each one and just multiply. Damn. I was so close to having something that was nice and same. Why not? If I really want to be pedantic, I should actually go back to the limit definition and try and use my limit to show you what the correct answer should be for the derivative of f times g. I think that is an exercise in futility and algebraic pain in the ass. So I'm not going to do it. Instead, I'm going to treat this visually. I want you to imagine as Babylonian, Egyptian, and Mesopotamian mathematicians did that our ideas represent length. So our function f of x is the length of a rectangle. Why a rectangle? Because f times g would then be an area. A length times a length gives me an area. So I'm going to picture a rectangle whose length is f of x and whose width is g of x. Now, in my limit definition, I would do f of x plus h, right? I would do g of x plus h. What would those do to this rectangle? Depends on the function f and the function g, right? Let's think of these examples. If you make x a little bit bigger, what happens to x squared? It also gets larger. If you make x a little bit bigger, what happens to x cubed? So I can say when I do x plus h, I'm going to get a little bit bigger of a length and a little bit bigger of a width. So we would add a little bit here, and we would add a little bit here. And then this is f of x plus h. And this is g of x plus h. And when I multiply those together, I get a bigger rectangle. And what I'm supposed to do is I'm supposed to measure the change in the size of this rectangle. That's what a derivative does. It subtracts those two and divides by h. I'm going to cheat. Again, I'm stealing directly from Babylonian, Mesopotamian, Egyptian mathematics. I'm going to chop this up into pieces. Remember our completing the square idea where we had those little extra pieces? I'm going to chop this blue section into 3 pieces. One piece, the one over here on the right, what's its length horizontally? Almost, because those are outputs of f. That's the difference between the big width and the little width. That's the difference in x values. But that's only the horizontal distance. What's the vertical distance of that piece? This rectangle here has a height of g of x. Now look at the rectangle across the top. The one that I drew really badly. What's its length? Just this part. Don't do the corner. Because I'm only looking at the inside. This is f of x, but its height is the corner is the weird part. Because the corner is going to have both of the changes, right? And my goal is to divide by h. Because that would measure the change there, right? But if I divide this whole thing by h, isn't that the same as dividing this part by h? And if I divide this whole thing by h, can't I just divide this part by h? But then I'd have f of x plus h minus f of x over h. Isn't that the derivative? Wait a minute. This rectangle, I'm only working with the derivative of f. I'm leaving g all alone. And this rectangle up here, I'm only working with the derivative of g and leaving f all alone. Here's the only place where I have to work with both changes at the same time. And that means that as I let h go to 0, those strips get smaller and smaller and smaller and smaller. But this strip only gets narrower in width. This strip only gets narrower in height. Its length stays the same. This one, its height stays the same. The corner becomes a dot. How much area is in a dot? So I can effectively ignore the corner, but I can't ignore those pieces. So when I really start to measure my change, instead of measuring both changes at the same time, I measure the changes one at a time. Let's go back to our example. F of x is x squared. Its derivative is 2x. G of x is x cubed. Its derivative was 3x squared. Instead of multiplying the derivatives together, I'm going to mix and match one derivative and one non-derivative. If I want to think of taking the derivative of the product, well, then what I'm going to do is I'm going to take the derivative of f, and I'm going to match that with g. I'm going to take the derivative of g and match that with f. Because then I will have added the rectangle that is the long, thin edge and the rectangle that is the long top edge together. Hey, what do you get when you do this? Hey, wait a minute, wait a minute, wait a minute. That's the right answer. In a paper from the 1700s, Gottfried Leibniz, one of the inventors and developers of calculus, has this picture. And this rule for taking the derivative of a product is known as the Leibniz rule, but I'll call it the product rule. That's easier to deal with. The product rule. If I want to think of them as the first function and the second function, rather than f and g, we'll call them f and s for first and second, then the derivative of a product is the derivative of the first, leave the second alone, then leave the first alone, and take the derivative of the second. I will often see this written with Leibniz's notation. You take the derivative of f, leave g alone. You take the derivative of g, leave f alone. I like the first version better because I like the prime notation better, but that's me. It's almost a mathematical catechism. The derivative of the first times the second, then plus the derivative of the second times the first. That's all this says. This works for every differentiable function, period. Which means I know how to do this. What is the derivative of x squared times e to the x? But wait, there's more, because that just took the derivative of the x squared. Then I have to take the x squared and leave it alone and take the derivative of e to the x, which fortunately for us is just e to the x. But I have to take the derivative of each function in turn. You had a homework problem like this. And I said, the easiest way to do this is to multiply it in. And then I can say, oh, well, I'm really taking the derivative of, well, wait a minute, this is x to the 1/2, so that'll give me x to the 2.5. And this will give me an x cubed. And then I can just use the power rule. But now that I have this additional rule, I can do it that way as well. First and second. The derivative of the first, leave the second alone, plus derivative of the second, leaving the first alone. Problem is I need to remember that derivative. Wait a minute, we wrote it up here. That's x to the 1/2. What's the derivative of x to the 1/2? Wait a minute. 1/2 x to the, because I have to subtract 1. And then the derivative of x is just 1. Now, your first reaction may be to look at this and go, this does not look anything like the stuff above it. And you'd be right. They don't look very similar. But with a little bit of algebra, multiply this in here, and that gives me 2x to the 3/2 and 2x squared and 1/2 x to the 2 minus 1/2, 3/2, and an x squared. How many x squareds do I have? How about that? And I have 2.5 of x to the 3/2. There it is. They match. Is that algebra truly necessary? Not at this point in time. But if I'm going to end up doing something with my derivative, then maybe I will want to do the algebra. But as far as I'm concerned, if I just say take the derivative, I want to see this line. And you can be done right there. Questions? Sometimes the fact that it can be done in either way doesn't actually help us out. each piece here is in a set of parentheses, which means if I really wanted to, I could FOIL this out. I apologize, I hate using that term. I could distribute, should be mathematically correct, and FOIL this damn thing out. But if I do that, what happens as the last? I'll get 3e to the x times the square root of x. And that's still going to need the product rule anyway. So is there any benefit to multiplying it out first in this case? I still have to do the product rule. If I leave it like this, I can do the product rule right here. I'll end up with something messy. But if I multiply it out, I might make a mistake in the multiplying. And then my product rule would have to be done on something that could be wrong. So I'm happier to actually do the product rule here. Derivative of the first. Leave the second alone. Plus, this time we leave the first alone and just do the derivative of the second. So now I can ask, what's the derivative of 2? 0. What is the derivative of 3e to the x? The constant stays there, and the derivative of e to the x is e to the x. Over here, what is the derivative of 1? Square root of x. We see the square root of x a lot. It's derivative of the square root of x. That is what x, the square root of x is. The square root of x is equal to x to the 1/2. Now I have to take the derivative. So I will just make that x to the 1/2 note up here. And then I can say, oh, the derivative of that is 1/2 x to the negative 1/2. It is important to be clear when you are making changes that are just algebraic versus when you are actually taking derivatives. When I go from the square root of x to x to the 1/2, that's just an algebra change. It's not a calculus change. Make sense? Okay. It is. That sucks. It's disgusting. Is there a way to make it nicer? No, unfortunately. No, that's going to suck no matter what I do to it, because I'm going to e to the x's times square roots of x in pieces. No, messy. Many of these exercises are rigged to be ugly. Why? Because I am a sadistic no, that's true, but that's not the reason. They're designed for you to practice. And the whole idea is not for me to suddenly turn into that meme joke about, the in-class exercise looks like 2 + 2, but the homework looks like an alien wears purple hats, how many cupcakes can Pedro buy for one human soul? No. The whole idea is that I want you to practice things that get progressively uglier. So that when you get to an exam and the thing is, oh, I've practiced here, but it's actually here, it's nice and easy. Questions? Yes, ma'am. Here? I've already taken my derivative. Any algebra I do after that is just algebra. Once I've taken my derivative, I'm done. But if I started with the multiplying out here, that would still be h. You'll notice there's no prime. 2 plus 2 square root of x plus 3e to the x plus 3e to the x square root of x. So I can take the derivative of this and this and this, but when I go to do that, that's where I need the product rule anyway. Other questions? If all it said was take the derivative, yes. No. Hey, you can stop right there. Any algebra you do should only be done for the purpose of doing something else. A legitimate question I could ask. At what x values does the graph of x squared e to the x have a horizontal tangent line? You were asked a question like this on Wednesday on the recording. Only we weren't working with x squared e to the x, we were working with some x to the fourth equation. The advantage is still having the papers in my pile. Yeah, if I want to know where the tangent line is horizontal, that's where my slope is 0. I take the derivative and set it equal to 0. We already have the derivative of this expression, don't we? Because we did this one earlier at the top of the page. But even if we hadn't, all we'd have to do is take the derivative, which definitely needs the product rule. The derivative of x squared e to the x was 2x e to the x plus x squared e to the x. And now I want to set that equal to 0. And Chloe, this is where I start doing the algebra necessary, because I'm going to do something with this derivative rather than just stare at it. Oh, 2x e to the x plus x squared e to the x equals 0. I'm going to factor. What can I pull out here? I can pull out an e to the x. I can also pull out an x. And that leaves behind a 2 and an x. In order to figure out where a thing that's being multiplied is equal to 0, I need one of the pieces to be 0. So either x is 0, e to the x is 0, or 2 plus x is 0. Well, first piece is already done. X is 0. Third piece. E to the x. To get rid of an e, you use an ln. That would take ln of 0. Grab your calculators, type in ln of 0. What does calculator say? Error, error, error. Old Star Trek computer voice. That never happens because if we remember the graph of e to the x, it's got a horizontal asymptote going towards 0. We never actually touch 0 at all. So there should only be 2 horizontal tangent lines. Draw me a picture. Let's check. Which am I looking for horizontal tangent lines on? That's not what I said. I want to look at the original. Show me a graph. Let's check for horizontal tangent lines. I should be looking at the original equation. X squared e to the x. kind of hard to see, but there's -2 and there's 0. Let's zoom in. Oh, okay. We flattened out up there at -2. We flattened out down at 0. Yay. As a matter of fact, if I hit trace, see my little blinker, and type in -2, we're at the top of that ridge. Yes, ma'am. Just hit the trace button and then type the number -2 and hit enter. If your calculator won't let you type on the trace screen, go to the calculate menu, hit second and trace. The first option says value. That's going to give you the value, whatever number you type in. If you hit enter, it'll actually ask you what value you want to type in. They did it on the home screen on the graph screen as a shortcut. But if you've got an older calculator, it might not work that way. But there's my -2. Is your -2 in the window? Hit your window. Yes, you must be looking at a point within the graphing window you are looking at. We can always diagnose your calculator at the end of class. Come see me right then, and I'll happily look at it with you, okay? Other questions? Okay. If I can do it for multiplication, you should be able to do it for division. If I look at f of x over g of x, that's 1 plus x squared over x cubed. I need no funny business to make this work. Again, you had a homework problem like this. And rather than me saying we're going to use some funky new rule, I just split this fraction up. 1 over x cubed and x squared over x cubed, and then rewrote it into being powers. And then I could use the power rule. F over g prime, derivative of x to the -3. Yes. And the derivative of negative x to the -1. Say a little louder, Jordan. -1x to the -2. Because I already wrote the plus, I'm going to put this in parentheses. If I hadn't written the plus, I could have just written the subtraction there. Again, I could do the algebra to simplify this. You won't see this answer in the back of the book. The back of the book hates negative powers, hates fractional powers, so they don't do any of that. Yes, absolutely. Because if I write f prime of x over g prime of x, I get 2x over 3x squared, which is 2/3 x to the -1, which is definitely not equal to that. So again, just like with my product, I see I can't just divide the top derivative by the bottom derivative. Damn, that would have been nice. So I have to do something different. And that's why I have to write it differently. Questions? So if that one was easy, why do I need a new rule? What happens if I look at g over f? I cannot separate this fraction. I cannot rearrange this fraction into a nicer version yet. So I'm kind of stuck with how to do this. If I really wanted to be pedantic, I would try and turn this into a product. And then, because multiplication and division are related, I should be able to use what I use for multiplying that way. I need another rule to be able to do that, and I haven't gotten there yet. But originally, that's the way this is shown. It's demonstrated through another rule we haven't gotten to yet. But rather than do that, I'm going to give you this rule as a freebie. Consider a top function and a bottom function. I want to take the derivatives one at a time. Derivative of the top times the bottom. And derivative of the bottom times the top. Dividing is the opposite of multiplying. So rather than add these, I subtract them. Order matters in subtraction. The most common error in quotient rule is to reverse these two. Do the derivative of the top first. But it's division. If I start with division, I should finish with division. And I'm going to divide by b squared. I promise this isn't an accident. This isn't coming out of nowhere. But in order to show you where it comes from, I need to get a little further. I'm just going to give it to you. Again, Leibniz's original paper has the illustration that I'm thinking of worked the other way. There's a long algebraic version of this. Ooh, very messy. But that means I can do this derivative. G over f prime. Derivative of the top. Leave the bottom alone. Minus derivative of the bottom. Leave the top alone. Over the bottom quantity squared. And again, 99.9% of the time, I get here, I'm done. It is usually helpful to simplify at least the numerator. I can leave the bottom perfectly fine as is, but it almost always makes sense to multiply out the stuff on top. In which case, I get 3x squared plus 3x to the fourth minus 2x to the fourth. Well, those I can subtract. 3x squared minus, no, plus 1x to the fourth. If I were going to do something like set this equal to 0 to figure out horizontal tangent lines, then a fraction is 0 where its top is 0. So if I want to look, where is this equal to 0? I only care about the numerator, which in this case, again, I factor. I only have one place. Because if I set each piece to 0 here, I get x squared equals 0, which gives me x equals 0, because the square root of 0 is 0. Here, 3 plus x squared equals 0 gives me x squared is negative 3, and that does not work. There is a way to deal with complex numbers in calculus, not this semester. That's a senior level course. We'll put it off till then. Graph the original equation G over F. Check. Did I get it right? G over F was up here. If you graph this graph, you notice something interesting. What do you see? What's your picture look like? It looks like it skips.
Like there's a cutoff.
Yeah. Around zero, it looks kind of weird, but the rest of it kind of looks like a straight line, right? So what's going on close to zero? Again, I will zoom in. My graph is flattening out and then starting to come back up. There's a bend in the middle of this picture. And lo and behold, we're flat right in the middle. Why does it look like a straight line? G over F. Always just looking at the original equation. Grace? This is an x cubed thing over an x squared. Remember we said if the powers were equal, we got a horizontal asymptote. And if the bottom power was bigger, we got 0. If the top power is 1 bigger, we have a diagonal slant asymptote. It does look like a line. And it doesn't just look like any line. It looks like the line y equals x. How can I check that? I am going to wrench your brains all the way back to your algebra class and ask you about division. Not just any division, long division. I heard that. How do you do long division? My calculator won't show me all the steps. It'll just stick out a number and go, okay, I'm done. That doesn't help when I try and do this. Because that's what our fraction is, right? It's x cubed divided by 1 plus x squared. Like this is 702 divided, 302 divided by 7. I need to do the division. What the? How many times does 7 go into 3? It doesn't. So go to 30. How many times does 7 go into 30? 4. 4 times 7 is 28. I subtract. Bring down the next term. How many times does 7 go into 22? 3 times 7 is 21. I subtract. I have a remainder. So I write a remainder over the divisor. If you used your calculator, you get 43.142857. And that 142857, 142857 keeps repeating because that's a seventh. You use them often enough, you remember them, but otherwise, I don't expect you to know that. But I can do the same thing here. I need to write the divisor in order of highest power. And the rest of the terms are zeros. There's nothing else under here, right? So all of those pieces are plus 0. How many times does x squared go into x cubed? It would be an x, right? X times x squared gives me an x cubed. So I put an x up here, and then I multiply. X times x squared is x cubed. X times 1 is x, and I subtract. The x cubes get canceled out, but I'm left with a minus x. As soon as the power of what's down here is smaller, I stop. Just like as soon as this was smaller than this, I could stop. There's nothing else to bring down, so I stop dividing. which means I would write x plus negative x over 1 plus x squared. Now think about this for a second. What happens as x gets bigger and bigger and bigger to this fraction? Higher power on the bottom, right? That's going to go to 0. Which means as x gets really, really big, it just looks like x. As x gets really, really negative, it just looks like y equals x. That's why it was the straight line that you said it was. It looks like y equals x. Because that's the part that doesn't go away. So y equals x is a slant asymptote, as opposed to a horizontal or a vertical one. It is also sometimes referred to as oblique asymptote. It doesn't just kind of look like y equals x. It actually really gets close to. And if we were to graph y equals x directly against this, we'd see that closing in as we go off to the right and as we go off to the left. Those graphs are going to get closer and closer to each other, aren't they? That's what asymptote means. Sympathy, to be like, to feel like, in this case, to look like. And if we go back further out, there's the graph of x cubed over 1 plus x squared. Look at how close they really get. They're very hard to tell apart. Again, the simplification isn't required. If I just say, take the derivative, show me you can do the rule, and walk away. I can ask you to plug in a number, right? Give me the slope at a point. We can find a tangent line. If I ask, what's the tangent line look like at x equals 1? You'd have to find the derivative at 1. I find my derivative, plug in 1. Do you need to be able to do this? Not yet. We'll save that for chapter 4. I thought I'd show it to you early. So, in about another 5 minutes, the homework keys will be posted. The review sheet key will be posted. If I don't have your homework, you need to give it to me now. And then I will see you all on Monday for the exam. Have a wonderful rest of your day.